Okay, welcome to the lecture series on electronic devices. And we are into the last part of module 5, where we are learning CMOS process integration. Today I will try to complete CMOS process integration, and we will try to look into another concept, that is integration of other circuit elements on the chip, like resistors and diodes and etc. Right. So, as a part of quick revision, let me quickly revise what we have covered in the previous class. That is, we had seen the concept of LDD, that is lightly doped drain. What is the importance of LDD? Here you are able to see in the fourth figure, some lightly doped drain has been extended. Yes. What is the use of that extension? Is it tries to prevent the damages happening due to hot electron effect. Now, what do you mean by hot electron effect? Is due to change in electric field, the velocity or kinetic energy of the electrons increases suddenly. Hence, those electrons become violent, or they move with very high speed and they just try to damage the drain. Okay, they collide and some internal structure it gets disturbed, right? So to prevent that, we just go with the lightly doped drain. Seen in the previous lecture, right? So moving further, that is next we are able to see uh, P substrate, right? This is one transistor. Okay, so in this transistor, we are seeing LDD on one side, right? LED is present on one side, and say this is P MOSFET, right? And in N MOSFET, sorry, this is N MOSFET, right? In P well, we have N MOSFET. This is N plus, and here also we have N plus. Okay, so this is N MOSFET, and here we are having LDD, right? To protect the internal structure from hot electron effect. And here, where in N well, we have P MOSFET, right? So what they are trying to show here, the LDD, it is optional for us, right? So wherever there is a chance of hot electron effect, yes, we can go through the LDD. And for LDD, we need to invest more because this is an additional procedure, correct? So there is no need to spend extra everywhere for that LDD. So what happens is, in N MOSFET, what are the majority carriers? Can anyone say what is the majority carrier in N MOSFET? Electrons or holes? Am I audible? Yeah, what is the majority carriers in N MOSFET or N channel device? What is the majority carriers? Holes or electrons?
Electrons.
Electrons.
Yes. So here in N channel MOSFET, we have the electrons, which are the majority carriers, and in P channel MOSFET, we have the holes, right? So the mobility of electron, it is more compared to the mobility of the hole. This thing we know, right? In the starting classes, we had seen this concept. Why? Because whenever an electron moves, right, then only a hole is generated there, right? So if this electron it is moving in this direction, after the electron has moved, then a hole is generated, right? So first initiation is by electron only. If electron doesn't move, then there is no hole. Therefore, we assume that the mobility of the electron it is high compared to the mobility of the holes, right? And by default, when we are saying that the mobility of the electron it is more compared to the holes, that means that hot electron effect will be predominant or it will be more in the case of n channel MOSFET. Why? Because majority carriers are electrons, and those electrons are having basically having more kinetic energy compared to the holes, or basically having more mobility compared to the holes, right? So the probability of hot electron effect in the p channel MOSFET it is less. Are you following? Yes or no? Yes or no?
Yes.
Others, please reply. Are you following what I'm trying to say?
Yes, sir.
Good. So, LDD it is usually preferred in N-type MOSFETs. Okay, it is optional for us, no doubt, but it is preferred in N-channel MOSFET or N-type MOSFET. Why? Because in N-type MOSFET, electrons are the majority carriers, which flows from one source to the drain, right? Hence, basically, we know electron has high mobility compared to holes. Hence, the effect of hot electron effect will be more where there are electrons, because the mobility is high. And the effect of hot electron effect will be less in p type, because there are holes, and holes basically have less mobility, right? So what they have shown here, in p channel MOSFET there is no LDD, correct? So there is no LDD here on the right hand side. And one more thing we are seeing here, the photoresist, right? So wherever there is doping, this thing we have already seen in in previous classes, right? Whenever there is doping, right, one transistor will be protected, because say this doping or this ion implantation of boron, if it is not required on the other side, then it has to be protected, and it is protected by photoresist that they are trying to explain here, right? And one more thing is there, uh, the p channel MOSFET it should have somewhat larger area compared to the n MOSFET, n type MOSFET. Why? Because of the same concept. See, the mobility of the electron is high and the mobility of the hole is less, correct? That means the current due to electron it will be more, because mobility is high, and collectron due to hole, yes, it will be less, correct? But when we are placing two transistors on the same platform, on the same substrate, then this should not happen. Why? If this happens, then there will be difference in threshold voltage. What is threshold voltage? The voltage at which the transistor starts working, correct? So in order to manage this, in order to compromise this, right, we will look into the point that the area of the p channel MOSFET it is slightly more compared to n channel MOSFET. Understanding? I'm speaking of width. If I increase the width, yes, the area will be increased. So width of the p channel MOSFET, it is seen that it is a bit higher compared to the n channel MOSFET in order to have same currents. Getting?
Yes, sir.
Yes, sir.
Okay. And it is generally seen that N plus polysilicon gates are used for N MOSFETs, and P plus polysilicon gates are used for P MOSFET. So where is polysilicon here? Right. So P plus for P channel MOSFET and N plus for N channel MOSFET. It is due to the property of that transistor. Okay, and we have graph here. So what this graph is indicating? This graph is telling net doping concentration versus depth. The doping concentration, right? And here we have the P channel MOSFET and the N channel MOSFET, correct? So the net doping concentration, it is more in P channel MOSFET compared to N channel MOSFET. Again, I said you it is due to this concept also. Okay, the electron has higher mobility and the hole has lesser mobility. And what is there in between P and N? In between P and N, here you are seeing, right? Here you are seeing this area that this is P well. Left hand side it is P well, right hand side it is N well. Let me clear the screen. Okay, so how this net doping concentration changes with the depth, right? So for P type MOSFET, we have uh, comparatively high net doping concentration versus depth, right? And for N channel MOSFET, it is comparatively lesser than the P type. In the middle of the channel, see here, this is basically the doping profile. Okay. So what do you mean by doping profile? For P type MOSFETs or P channel MOSFETs, how will be the doping profile or doping concentration? And for N channel MOSFET, how it will be? Okay. And in the middle, we are having decreased doping concentration. Why? Because there is junction of P well and N well. Okay. So where there is junction of P well and N well, there we find that what is there? Basically, what is there when P and N touch each other? It is the formation of depletion region, right? So depletion region will be formed here. It is not shown exactly, right? But here, wherever P and N they just intersect, there will be depletion region. And in depletion region, we know that there is no movement of charge carriers or there is no current, right? Hence, this doping concentration it is decreasing here, right? Why? Because there will be recombination. There will be recombination at this point. So nothing um, uh, much in depth is given for this graph. You have to understand how the doping concentration changes for P and N and why there is uh, decrease in doping concentration at the junction. Understood?
Yes, sir.
Next graph we have electron energy versus the depth. So this is Fermi energy level. This is valence band This is conduction band, right? So what happens? What do you mean by Fermi energy level? Fermi energy level, the probability of the energy. Okay, it is probability of the energy wherein the charge carriers can occupy that energy, right? So the Fermi energy level for electrons, it will be near the conduction band, or for N type, it will be near the conduction band, and for holes it will be near the valence band, right? So we are speaking of electron energy now. When we speak of electron energy, the Fermi energy level, it will be near the conduction band. Why it is so? Because electron, it tries to jump from valence band to the conduction band always, right? So probability of electron is more near the conduction band, not in the valence band, right? So whenever we just try to operate any device, the electrons we will find more in conduction band, not in the valence band. And here you are seeing actually holes are being collected, right? Holes are being collected in the valence band. What do you mean by holes in the valence band? When holes will be appearing in the valence band? Am I audible?
Yes, sir.
When hole will appear here in the valence band? When any electron, it jumps from valence to conduction, then only hole will appear. Yes or no?
Yes, sir.
Yes.
So this graph, it is telling us that the electrons, they have the probability of jumping from valence band to conduction band. Hence, there will be accumulation of holes in the near the valence band, right? And actually, they have written here buried channel and surface channel. That part is not given in depth, right? What is that buried channel and all? No need to worry. I'm telling you the gist of the uh, graph, right? The graph is telling us that in any semiconductor, right, the Fermi energy level for electrons, it will be near the valence band. Why? Because always the electrons try to jump from conduction, sorry, valence band to the conduction band. The Fermi energy level will be near to the conduction band. And because of shift in the electron, when they gain some energy, they just jump from valence band to the conduction band. And when they jump, there will be collection of holes. That's it, right? And this is one more diagram. Actually, this is the another view of the fabrication. Like this is the cross sectional view of LDD MOSFET with the gate length of I think 52 nanometers. So this one, right? This is the cross sectional view. So how that LED is formed, that they have shown, right? But there's no need to represent this in the examination, right? No need. So they are showing how LED is formed, right? Here we have LED. That LED they are showing here. Next comes integration of other circuit elements. This is the last topic. Integration of other circuit elements, right? So first we will take integration of diode. Now, what do you mean by integration of other circuit elements? What do you mean by integration? Bringing together. Are you following?
Yes, sir.
See, we have substrate, right? On that substrate, we will have transistors, correct? So in this region, we will have one transistor, one T. I'm writing one T here. And beside that, I'll have one more transistor. I'll write second transistor, that is 2T, right? And say, imagine my circuit requires one diode here, one D, right? So how to fabricate the transistor that we have seen. So module 5 consists of all the steps, right? How that transistor should be fabricated on the substrate, correct? But how to fabricate this diode, right? Diode we have not at all seen till now. How to fabricate this diode? Say if my circuit is having two transistors, one diode, one resistor, then how to fabricate that diode or how to fabricate that resistor onto the substrate? This is nothing but integration of other circuit elements. Apart from transistor, what are other circuit elements? The diodes, capacitors, resistors, inductors, then contact cuts and all, right? How those things can be integrated on the same chip. That is integration of other circuit elements. So first thing we are taking, that is nothing but integration of diode, right? Did you follow?
Yes, sir.
So diode, it is basically a two terminal device, right? It has anode and it has cathode. We want to incorporate this diode on the substrate, right? Maybe p type substrate or n type substrate, anything. So we will not bring the diode. We will not bring the diode, right? Why? Because see, all the fabrication steps, they have to be repeated. They have to be followed for the transistor, right? And after the transistor, again, if you want diode, again, few of the mostly all of the steps have to be followed for fabrication of diode also, right? So there will be repetition of the steps, unnecessary repetition of the steps. So what the fabricators they do is they just try to modify the transistor which will act like diode. Okay, so transistor, if I make a transistor, right, and if I modify something in this transistor so that it can behave like a diode, then our job is done. Why? Because uh, anyhow we will be fabricating transistors on the chip, right? There are so many billions of transistors, and one of the transistor that can be used as a diode, if I make some modification in the transistor so that it gets the characteristics of diode, it behaves like a diode, then our job is done, right? So for that, what we have to do? For that, see how we represent transistor. It is NPN, right? So this is N, this is P, and this is N. This is a transistor. Now I want to convert this transistor into a diode. Say this is emitter, correct? Then this is base, then this is collector, correct? Now what I want to do, I want to convert this transistor into a diode. Okay. So how to do that? One thing we can do, base and collector we can short. If I short base and collector, right, it will not behave like P and N now. Why? Because the least resistance path we have given here, correct? So when I short base and collector, our transistor will behave like a diode. So in the process of fabrication, we will follow the same steps. Like here, I said you, I need two transistors. It is 1T, 2T, and here I require 1D, right? So I'll not go with that D. I'll go with the T only, and after that T, I'll just protect these two transistors, right? And then what I'll do, I'll do this short connection, right? I'll just simply interconnect base and collector, so that only third transistor uh, gets converted into diode. Following? Is it understandable?
Yes,
Yes.
sir.
So how this will behave like a diode, you just try to think over it. Okay, take this as homework. When I simply short base and collector, or you can Google it also, right? Converting a transistor to diode, how it will behave like a diode, right? What happens if I short base and collector? How it will behave like a diode, right? That thing you can take it as homework. Then next we have integration of resistor onto the substrate. So we have integration of resistor onto the substrate. So now what is resistor? Again we know resistor, it is a two terminal device. But again transistor, it is three terminal device. Correct. So emitter, base and collector. Right. So how this transistor can be made to behave like a resistor? How is it possible? Yes. Any thoughts on this? Any ideas? We have to reverse bias. We have to see whenever any PN junction, if it is reverse bias, what it will behave like. PN junction reverse biased. Does the current flow through it? Does
No, sir.
majority? No, there is no current flow, right? Why? Because whenever PN junction is reverse biased, depletion region gets widened, which will behave like an resistor. What is work of resistor? To resist the flow of current, to control the flow of current. Correct. Here also, we can modify this transistor. We can reverse bias it on the junctions where the depletion width can be controlled. Okay, so the amount of reverse biasing can control the width of the depletion region, and that width of the depletion region can control the resistivity in turn. So if there is more reverse biasing, more width will be there, right? Depletion region will get more widened, and when there is more widened region, then that depletion region will be having more resistance. Correct. So depending on what amount of resistance we require, we can model it. Yes, we can customize it. So how that is done basically? So during implantation, that is base implantation, right? Where is the base? Here is the base. Correct. When there is base implantation, what thing happens is a resistor can be implanted, which is made of very thin p-type layer with one of the n-type islands, and alternatively also a p region can be made during the base implant, and a n-type resistor channel can be included within the resulting p region during the emitter implant step, right? So here what we are doing in base implantation, we are just implanting uh, very thin N-type resistor channel, right? And also we are implanting very thin P-type layer. So here in this we are having PN junction, right? In the base only we are just trying to create PN junction, and you just try to reverse bias this junction so that it will behave like a resistor. Basically resistance is the property which is there in each and every material, right? But the thing is we have to control that resistance. Say if I require 1 kilo ohm resistor, right, then this resistor which is being created by implantation of P and N in the base, that should be having that resistance, right? This is more important rather than what procedure is followed. And how it depends, actually resistance, it depends on what? Resistance, it depends on what is the formula? Rs, resistivity, it is rho into L, yes, divided by
Area.
area, or W into T, or you can say it is area, right? Area means it has W, correct? So how to control that resistance? Resistance can be controlled by controlling the length. What length? Length of the PN junction, which is being implanted in the base. And it also be controlled by controlling the area. What area? Area of that PN junction, right, which is being implanted in the base. So length and width can be controlled to get the controlled resistance, required resistance value. Are you following?
Yes, sir.
So even thickness also, right? Length is different, width is different, and thickness is also one parameter, right? So all the three characteristics can be changed during the, or can be set during the implantation to get the required resistance.
Sir,
And that, yeah,
temperature can also be a factor no? To
yes,
control.
yes. Actually, the resistance, it changes with the temperature, right? Hence what happens generally, we see that if any device it is getting overheated, then we have to cool it. We have to make some arrangements for cooling that device. Otherwise what will happen? Otherwise it will change its resistance, right? And when resistance is getting changed, that means the current will change. Current which is flowing through that device will change, right? And if this thing is happening, it is more dangerous for the device. Say you take the example of any mobile, right? You use it continuously, it will get heated up, correct? It will get heated up, and if you do not stop using it, oh, what will happen? Some IC will get damaged. This is what we generally see, right? So the very reason, or the very bad enemy of the electronics is heat only, right? So even in the laptops you see, or even in the PCs you see that fan is provided to exhaust the heat, correct? So even temperature, it plays a very important role in changing the resistance, correct? So for every 10-degree rise in temperature, the resistance it gets changed. So the temperature should also be maintained. That is the external factor, right? But internal factors, we are speaking about the length, the area, right? So say if I want 100, say 1 kilo ohm, correct? Then I'll set the area, I'll set the length of the PN junction, right? The length and width of the PN junction I will set, and as per that length and width, if I'm able to achieve this 1 kilo ohm resistance, right? And then what will happen? If some external parameter like temperature it is trying to change this, then our device will get damaged. Otherwise, your electronic devices, it may never get damaged if you are uh, playing with it safely, that is within the temperature range, right? Each and every electronic component, it gets damaged only due to heat. That is widely seen throughout the world. Following? Understood?
Yes, sir. Yes, sir.
So this was about the resistance, right? Then we have the next thing, that is capacitors. Capacitors on integration of capacitors on the substrate. Integration of capacitors on the substrate. Say like resistor or like this diode. See, if I require a circuit where I need one transistor, one diode, one resistor, and one capacitor. Correct. So I have to convert the transistor into capacitor now. I have to convert transistor into capacitor. Separately bringing the capacitor and integrating onto the chip, it will cost very high. So the basic element is transistor. We have to convert transistor into the capacitor, like we have done it for diode and resistor. How to do it? It's very simple actually. What is there in the transistor? What do we see? There is silicon dioxide, correct? SiO2, which is nothing but an insulator, correct? Then we have, so here SiO2 will not come. Here we just do the etching, and what we do, we just ion implant the P type or N type material that will create the source and drain, correct? So this part, the doping is done or the ion implantation is done, so that here we have source and drain. So this is source, this is drain, and then this is SiO2, correct? This is SiO2, and then above that we have gate, that is polysilicon, right? G for gate, right? Now what we are having? We are having a layer where inversion takes place. So it is like this is SiO2, and above SiO2 we have gate, right? So this is gate, and below this SiO2, say this is SiO2, and below this SiO2 we have one more layer, that is the substrate layer, right? So this is like metal oxide semiconductor, MOS. Are you understanding? I have zoomed this part. Able to imagine?
Yes, sir.
So if you simply look at this structure, it is like capacitor only. What is metal? Metal is one plate of the capacitor. What is substrate? Substrate is second plate of the capacitor. What is there in between? Dielectric. Correct. What is the dielectric? This SiO2 itself is the dielectric. So it is simply like this. Here we have the gate. Here we have the body, that is substrate. Right. So here charge carriers will be there. Correct. Maybe electrons, correct? And when I'm saying that here we have charge carriers, right? Then on the other side we will have some potential, that is the other charge carriers. Getting? So it is basically transistor, it is like a MOSFET only. We have seen MOS capacitor. Before the we started with the MOSFET, we initially took the part of MOS capacitor. That means the transistor, before it behaves like a transistor, basically it is one capacitor only, right? So it is very easy for the fabrication of capacitor onto the substrate, right? That transistor, it can be converted into capacitor. So how to convert that? We will simply short some lines, like uh, we have the, so where the capacitors are used, before that we have to see where the capacitors are used generally. What capacitor does? What is the work of capacitor? Yes, anyone please? What is the function of capacitor? What it does? What is capacitor?
Stores the charge.
Correct. Very good. Very good. Very good. Capacitor stores the charge. Correct. Now, what is that charge basically? What is that charge? If you go into the digital electronics or your digital system design subject, right? So here in that subject you play with 0 and 1, correct? Either the output is 0 or the input is 0, the output is 1, right? Like that. So this 0 and this 1, they are nothing but charges only. They are nothing but charges only. When there are charges, that is 5 volts, there are charges, we say it is 1, or when there are no charges, we say it is 0, correct? So we have RAM, ROM in our mobile phones, correct? So this RAM or ROM, it will have memory, correct? RAM or ROM, they are the memory chips, correct? So what is the function of that memory chip? To store the songs, to store the images, to store the videos. Yes or no? How it will store? It will store with the help of capacitor only, right? So your each and every pixel in the image or your each and every word or that song, whatever it has, right? Each and every part of the song, it is nothing but charge only. Either it is 0 or it is 1. Understanding?
Yes, sir.
Yes, sir.
Yes,
So
sir.
memory, the RAM or ROM, we can store the videos, audios, images, and all, right? So all those data, maybe video, audio, or image, all those data are in the form of 0 and 1 only, and that 0 and 1 has to be stored, and it can be stored using this MOS capacitor, right? So all the memory chips, it has the MOS capacitors in it to store your data, data in the form of 0 and 1. And what is basically 0 and 1? Everything which we see, which we hear, right? Audio, video, images, everything, it is in the form of 0 and 1. It is converted in the form of 0 and 1 to store, right? Why it is so? Because storing the analog value, it is very, very difficult, but storing the digital value, it is very, very easy comparatively. Hence the analog, see, basically song, it is an analog, like it has pitch, it sometimes the pitch goes high, so sometimes the pitch goes low, correct? Basically it is analog signal, but it is converted into digital. Why converted into digital? To store the to store that data, right? Once it is converted into digital, it is very easy to store that 0 and 1, that is digital data, and it is stored with the help of MOS capacitors, and these MOS capacitors are present in the RAM and ROM, right? So basically in RAM again we have DRAM, SRAM, all those things we will study in the upcoming semesters, but static RAM, dynamic RAM, and all that I was saying, right? So basically what is the funda here? We want to integrate capacitor onto the substrate. That can be done very easily by this modifying a transistor, right? So what we have to do, let me clear the screen again. So if you want to uh, fabricate the capacitor onto the or substrate, or if I want to modify that transistor into the capacitor, right? Then what we do, we have basically this transistor, correct? So this is SiO2, and above that we have the gate. So this is gate. This is source, and this is the drain. So this is the transistor, right? And if you want to convert this, right? So we have the word lines and the address lines, bit lines. We have the bit lines and the word lines. This thing I think you might have studied in computer organization. I'm not sure about it. So in the memory we have bit line and word line, correct? And so here one will be the bit line. Bit line means what? Bits, right? 0 and 1, they are nothing but bits, correct? So or basically we say that it is data bus and address bus. Have you heard of these two terms? Data bus, address bus.
Yes, sir.
So data bus means what? The bus which carries the data, right? So here the data will be moving in the data bus, correct? Basically, we are naming it as bit line here, right? So either 0 will come or 1 will come here, right? That has to be stored, correct? So when that 1 comes here, correct? Say 1 has come from this bit line, right? So 1 is stored here, correct? And on the other side, say from the word line 0 has come, so 0 will be stored here. So this 1 is stored here and 0 is stored here, right? In between, what we have, in between we have SiO2, which is acting like dielectric. So the structure is looking like this only. Yes, getting.
Yes, sir.
So this is how transistor can be used as a capacitor. So there is no need to integrate separately the capacitor onto it. Then we have the integration of inductors onto the chip. Basically, inductors were not used for so many years, right? On the chip, we never used to have inductors. But nowadays, due to RF analog ICs or for portable communication, right? In the communication subjects, we use RFICs that we will again study in the coming semesters, right? So in that RFICs, we have some integrators, right? So actually, there was no need of there was no need of inductor. There was no need of inductor for these many years. But recent developments in RF domain, it has created the need, and we have to do it, right? How that inductor can be fabricated. Basically, what is inductor? It is nothing but spiral wound, right? It is spiral wound. Any wire, if you simply spirally, if you wound it, if you wind it, right, then it will behave like an inductor. So it can be fabricated using spiral wound thin metal films on that IC. Spiral wound thin metal films, right? Metal films means what? It is basically like wires only, right? Thin wires. And spiral patterns can be defined by photolithography. See, the spiral thing should come, right? Again, that can be done by photolithography by using the mask. In that mask, we should have spiral thing, right? So that spiral thing can be imprinted on the chip using that mask. So by the process of photolithography, even fabrication of inductors onto the chip, it is possible nowadays. Photolithography followed by etching, correct? Just like we have the mask for rangolis, if you have seen in the markets, right? So mask for the rangolis, like we have mask for the inductors. Understood?
Yes, sir.
Okay. So last part is integration of contacts and interconnections. Like I said you, on the chip, I require one transistor, second transistor, diode, capacitor, all these things. But something should be there to connect it, correct? So that something is nothing but interconnects and contacts. So one resistor, it has to be connected to a transistor, right? Then that can be done using interconnects or contacts. So contacts and interconnects, they are basically done by metals. Maybe aluminum is commonly used for top metallization, or you can say simply connection between the two devices or two components. It can be done using metal. In metal, aluminum can be used, gold can be used, right? But gold, what is the rate of gold? If we use gold in the ICs, then your ICs it will cost more, right? So because of cost, we do not prefer gold, but we just prefer the aluminum, or sometimes copper is also used, right? So aluminum, copper are the best conductors for these contacts and interconnections. And because of their properties, electrical properties or resistivity properties, again here also they have given the formula of resistance, right? So I have written it already. but because of its electrical and resistive properties, these two metals are widely used for interconnects and contacts. And one more thing which is there here, right? See, whenever I connect the resistor with the say transistor, okay. So if this connection I have and I have connected it, when I connect, right, this part of the wire or this part of interconnect, it will also have some resistance. Yes or no? Are you following?
Yes, sir.
So this part of the interconnector wire, it also has some resistance in it because it is not a superconductor, right? So this resistor, it will cause some delay. This resistor of internal wire, it will cause some delay, right? Actually, we call that delay as time constant T, which is nothing but product of R into C, right? So basically say here there is resistance, right? Here this is resistance. This is internal resistance of the wire. Correct. This is the internal resistance of the wire. Then what we have? We have transistor, right? In transistor we have capacitor. Getting? Where is capacitor? This is nothing but gate. This is the gate. Say this is the gate part and this is the substrate part. Between gate and substrate we have capacitor because there is silicon dioxide, correct? So we are seeing something like resistor, internal resistance, then capacitance, then we have the transistor. Are you understanding?
Yes, sir.
Yes.
So this is unwanted, okay, and this is unavoidable also. We cannot avoid it. Namak badappa ತೆಗಿತೀನಂದ್ರೆ no, it is not possible. Right, it is not possible to remove the internal resistance and capacitances. Those are called as parasitic capacitances, right? So but what did I say you? Delay, it is product of R into C, right? So if the internal resistance of this wire it is more and if the capacitance of the transistor it is more, then it will create some delay. Delay means what? If I am giving signal 0 here, right, at 1 nanosecond, it may reach this part say after 4 nanoseconds. So 3 nanoseconds is the delay between this. This is just an example, okay? Basically it will be in picoseconds. It will be in picoseconds because these R and C which are present here, right? No doubt they are unavoidable, but we can try to reduce it. We can try to reduce this R and C. How we can reduce that R and C? We can change the width of the conductor which is connecting resistor to the transistor. Following?
Yes, sir.
Yes,
So,
sir.
so this time constant R and C, it plays a vital role in the VLSI. That is integration, right? And here you are able to see what is this? This is nothing but capacitance everywhere in the substrate. Between each and every between each and every connection, we have the capacitance. See, metal to metal connection, there is capacitance. Why? Because there is dielectric in between. Again, metal to contact, there is capacitance here. Then contact to polysilicon gate, capacitance. Correct? Again, here also we have capacitance. Then metal to the polysilicon gate, again we have capacitance here. Correct? Then metal to the drain or the source, we have capacitance. Then channel, between channel and between the metal, again we have capacitance. So everywhere this capacitance exists, which is parasitic capacitance, and it is unavoidable. Okay, it may be unwanted, but we cannot avoid it. Everywhere we have capacitors, which is actually it is present in the material only. Okay, we have not inserted any capacitor. It is being fabricated or it is present in the fabrication step only. It comes, right? So it can't be avoided. Thank you for listening. So we are just winding up the module 5, wherein we are into the understanding level of L2. Right? Thank you, everyone.